What you doing, boo? Hmm? What you doing? Okay, just so we can get started on time, if you go ahead and type your name in the chat for attendance, that would be awesome. Okay, for those of you just joining, go ahead and type your name in the chat. Okay, I know it's Halloween. Sorry for doing this. I wish I could have postponed the class or made it some other time, but unfortunately, that falls into other people's calendar issues. Um, so, for those of you that are handing out candy, I'm so sorry. I know looking at the kids in their costumes is, one of the most exciting things about it. Plus, eating the leftover candy isn't bad either. But, um, oh, you can't hear. Can anyone else not hear?
Doctor, can you hear me?
I can hear you.
Can you hear me?
Yes. Yes. Okay, is there
I,
anybody that can't hear me? Okay. I'm wondering if I don't know what it was. He's probably going to get back on. That's fine. Okay, so I'm going to go ahead and get started. The first thing I want to do is I want to go over the um, the mastering physics. Um, I have quite a few students that are enrolled in the course and coming to lecture, but I'm not getting any of the assignments. And so I want to make sure that you understand where to go to get your assignments. For me, when I go into my Google, I automatically have the most important things right here. These two things are the most important. Uh, Logging into the college website and accessing Mastering Physics. So when you sign into Mastering Physics, you should be clicking on the link. And when you do, you should see your classes. If you have just mine, it'll be this one. If not, you'll see other ones. Once you go in, you should see these assignments. And like I said, I have a couple of people that are enrolled in the course. They're attending.
Doctor, I still can't hear you. Can you hear me?
Yes. So I'm not sure what's going on with Andy not hearing. Okay, he might have to work on the audio. Um, so if you don't recognize this, then most likely you haven't been getting into the mastering physics and doing the assignments. So, for instance, I have the intro to mastering, which just goes over how to answer the questions. Then I have some reading assignments. I stopped doing those because there was a lot of things that they wanted you to do while you were reading, and I felt like that was just too much. And I didn't want to overwhelm all of you. So if you're reading through the online chapters, that's great. Here is a study area that you can go to. Uh, Here are my resources, uh, and then my tools, which allows me to look at your work and grade. But anyway, here are the assignments. So please make sure that you're doing these assignments where it says dynamic study modules. Okay. Some of these are going to notice that they're past due. So please make sure that you're doing them in a timely manner. If you have not registered for Mastering Physics yet, keep in mind that the lab component also goes with the course. And this also is your participation grade. And this is where you're going to see your tests show up. So you need to get into Mastering Physics. Okay, so that's it for Mastering Physics. If you need help with it, my office hours are Tuesdays. It's now 6 to 7 instead of 7 to 8. It just works out a little better. So now what we're going to do is we're going to go ahead and start with the lecture. Let me show you something first. Nope, wrong one. So your lecture notes should be in there. Okay, so when you come into the course, oops, wrong one. I don't have the lab set up in the lab course. You can access it through this course, and then there will be a link later tonight for you to upload your answers. Okay, so for today, we are doing module 6. So all of the items that are listed here are due by next Thursday. Okay, so we're going to be covering these topics tonight. Here are the lecture notes if you want to have a copy of the lecture notes to fill in the blanks. Here is projectile motion and satellites. This is actually a quiz. And so instead of you doing the discussion board this week as your participation grade, I'm giving you a quiz. You are allowed to use your notes, but understand that this is a timed quiz, and I believe I've given you 30 minutes for 20 questions. Your lab is a made-up lab. I do want to go over quickly what you have to do. You'll need a rubber band, and some paper. So there's multiple things you can do. You can take the rubber band between your pinky and your thumb and shoot it. Shoot the paper ball that way. So if you hold it like this, you can shoot the paper ball, and then you'll need a protractor and a ruler. If you don't have a protractor, I'm okay with, actually, you could even do these fingers. I'm okay with you saying, okay, this is about a 30-degree angle, this is 45, this is about 60. Okay, you can kind of guesstimate as long as you don't continue to move your fingers like this as you're doing it. Read through it. If you have any problems, do not wait until Thursday to ask me the questions. Please read through it sometime between now and Tuesday so that if you do have some issues, you can come and see me in office hours. I think to make it easy for everybody, everybody can get into Zoom. I'm getting some people trying to get into Zoom for my office hours. So I think what I'm going to do is I'm not going to use Workplace anymore. I'm going to just go ahead and use this same Zoom link for the office hours from 6 to 7 on Tuesdays. And I think that'll just make it easier for everybody. I didn't get any feedback on that, but I'm hoping that I do. That my decision to go to Zoom only will be okay with everyone. Okay, last week you had the lecture notes, the dynamic study module. There will be a dynamic study module for projectile and satellite motion. I just didn't get it here, but just know that you always have a dynamic module and it's already set up in Mastering Physics. Okay, so tonight we're going to be doing satellite and projectile motion. Okay, and hopefully I gave everybody enough time by chit-chatting with you about assignments that everyone has the lecture notes up and running now. Okay. Oh, okay, good. I was going to say the other solution when you can't hear me is to actually connect your audio by phone. And that seems to work for me.
I had to shut it all the way down. I shut the computer all the way down and started it back up.
Oh, okay. That's another thing. If you filled your cache, that can also do it. It causes your computer to go wonky. You just go into your internet and you clear your cache for your internet, and all of a sudden everything works fine again.
All right, thank you.
Mm-hmm. Okay, so here are the objectives for tonight. We're going to talk about projectile motion, fast moving projectiles, which are satellites, circular orbits, and then we'll go into elliptical orbits and how they're different and the same. And then we'll talk about Kepler's laws of planetary motion, the energy, and satellite motion. So energy is conserved for satellite motion. We'll talk about that. And then what escape velocity is, or escape speed. Oh, I'm going too fast. There we go. Okay, so without gravity, a tossed object would continue in a straight line path. We learned that when we looked at forces, right? So if I throw something, the only reason it goes down is because the earth is pulling it down. Okay. With gravity, the same object tossed at an angle follows a curved path. And we call that curved path a parabola. Okay. So the shape of the parabola is the same on both sides of the highest height. Any object that moves through the air or space only under the influence of gravity is called free fall, right? We've talked about that. But when you have it just vertically up and down, that's the free fall. But projectile motion is when you take that free fall and add a horizontal component. Okay. And so that's what gives it that parabolic shape. Okay. So if you've ever watched baseball, if you watched the World Series last night, and you saw the hits, typically if they're going to be a home run, you see them arcing up and then they start coming back down, and that's your parabola. There's a little more to it because baseball is a little, it's got rotational dynamics involved in that, which changes things. But for all intents and purposes, it'll be a parabola. Okay, so if you look at this diagram here, what you see is in the first picture, you're going to see a ball that moves off of the table, but without gravity. Okay, notice that the horizontal speed and the distance it travels is the same. It's not changing. And that's because there's no force acting on it horizontally, right? There's nothing physically touching it and nothing acting at a distance. If you look at the second picture, here you have the ball just physically dropping. And this is what we call free fall. Okay, so here we are, now we have gravity, the ball goes straight down. If you look at the last picture, we have that horizontal motion, which notice the same distance for every time interval, the same speed for every time interval. Okay, it's going to be like a ball rolling across the floor at a constant speed. But you're also adding that drop. And remember, even though the speed changes the same amount, 10 meters per second every second, your distance does not. Remember how we had to do that t squared part, okay? So instead of it being 0, 10 meters, 10, 20 meters, 30 meters, that's not what happens. It's 0 displacement, then 5 meters. Then we have 20 meters, right? It's going to be 2 times 2 is 4, times 10 is 40, divided by 2, which gives us 20. Okay? And so remember that it kept the distance, kept increasing and increasing and increasing as you fell, the faster you go. So this leads us to having that parabolic shape. The horizontal will always be the same. The vertical changes, it's quadratic, and that's going to give us this parabolic shape. Okay, so projectiles that are launched horizontally only have the force of the Earth acting on them. So typically we ignore air resistance. Now, if you are working for the military and you're shooting shells out of a tank, you really do have to worry about air resistance. Hopefully, the things that you're launching are made so that they are aerodynamic, but you can't get rid of all of the wind. A lot of times they'll have a nose cone on it so that the air flows around it. But at the back end, you're going to get what we call non-laminar flow or chaotic flow. And that's going to cause some problems. So when you're launching things really, really fast, you're going to have to take air resistance into consideration. But if you're just throwing a ball back and forth, not really. Okay. So the only force that's acting on it is going to be the Earth. The horizontal component will not change because there's no forces acting horizontally. Vertically, though, you have the Earth acting on it. So it's going to increase its speed 10 meters per second every second. Now, keep in mind, this is where the vectors come in. Horizontally, you move 5 meters. Vertically, you move 5 meters, right? Horizontally, you move 5 meters. Vertically, you move 20 meters, okay? So you're going to see that it's going to give you that shape. Okay, so horizontally, as you can see, the gravity force is down. The projectile accelerates down. As the projectile travels, it increases its vertical distances in equal time intervals, but it also increases horizontally at the same time. And this is what makes it difficult for students. They have trouble separating that horizontal movement with the vertical movement. Just remember, you can't add anything together if it's not in the same direction or if it's not perpendicular, okay? And so that's the only way you can add things together when you're talking about a direction. Okay, so I've been using this word over and over and over again. It rises rises from the ground with a vertical and horizontal component. It accelerates as it moves up. It comes to the top of its motion. Notice it's still moving. Okay, it's still moving horizontally. It reaches the top of the curve, and then it starts to sink. Notice the vectors here. I'm gonna, I hope this is my pointer. Yep. Okay, so notice here the horizontal component is the same for all time intervals. Okay. So the horizontal velocity doesn't change, but look at this. This is like 20, this is 10, this is 0, this is minus 10, this is minus 20. Be careful. If I asked you, what is the acceleration at the top? Well, there's no acceleration in the horizontal direction, but isn't there a force in the vertical direction? Yes, you have the Earth. If you took away the Earth, this would start moving horizontally and it wouldn't stop. It wouldn't come back down. Okay. So remember, even though your vertical velocity is 0 at this point, you still have acceleration. Okay. Notice that the horizontal component is also there. So even at the top of a projectile, you can't say that the velocity is 0. Okay. It has an actual amount. Now, when you take projectiles and launch them at different angles, the path is going to change. Okay, so if you look at the left-hand picture, you'll see that the horizontal motion would be, if there were no gravity, it would just go straight up. Okay, But notice that from that straight up position, it drops 5 meters, then it drops 20 meters. And then the next one is 3 times 3 is 9, 9 times 10 is 90, 90 divided in half is 45 meters. Okay. So notice that it's going to drop from this position here and go down that amount. Okay. When you launch it down this way, it's going to hit the ground sooner. And notice it's not going to move as far away from the cliff. And that's because now you're moving 5 here, okay, 20 there, 45 here. And notice it's going to be lower because of the fact that you are angling it down instead of up. This should automatically make sense anyway, right? Everyone knows that if you throw something up in the air, it's going to take longer to hit the ground than if you threw it straight, or diagonally down. Okay. But this just shows you graphically why that's the case. Okay. Notice that horizontally, you have the same segment here, here, here. Notice horizontally, same segment. It's being launched with the same speed, but a different angle. Okay. So horizontally, it's the same. It's the vertical part that's going to change. Okay, so here we have a cannonball that's being shot upward at an angle. The vertical motion, again, is identical to the cannonball that gets launched straight up, hits a 0 velocity and comes back down. Okay. And remember, still acted upon by the earth, no matter where it is in the path. Horizontally, though, it's going to stay the same. Okay. So horizontal position is going to increase this way horizontally, but the same amount. So notice here, here, and here, that's the same distance, right? But notice that the drop goes from 5 to 20 to 45, okay, from that horizontal line at that angle, okay? And that, again, gives us this parabola. I just think this is so cool that these diagrams show you that if you were to launch this just straight, it would go a straight amount of distance for every time because there's nothing acting on it. And then because of the equation, remember that 1/2 GT squared, this is what you get, the actual path of it. Okay, so the velocity vector at each point here is resolved into the horizontal and vertical components. And you can see that they've drawn a parallelogram for that velocity vector in order to give you the X and Y pieces, the X and Y components. So here you have the horizontal component. Notice it's the same for every single point. This is 1 second or 0 seconds, 1 second, 2, 3, 4, 5, and 6 seconds. And then notice here that the vertical decreases by 10 meters per second every second. Okay. The horizontal component, again, will stay the same because there isn't anything acting on it. The vertical component, though, has its highest amount at the beginning and at the end. Notice here, there's what we call symmetry. This may be 30. This is going to be negative 30. This is positive 20. This is going to be negative 20. This is positive 10. This is negative 10. And this is 0 for the vertical velocity. Okay. So the magnitude of the vertical component of the velocity will reduce until it reaches its maximum height, where it becomes 0 at the top. Okay. It then will increase its speed as it starts to fall back down here. And then again, you can come up with the components by using sine and cosine, but you can use a parallelogram here and Pythagorean theorem to actually calculate the value of the actual velocity if you know the horizontal and vertical pieces. Different distances or different horizontal distances can be achieved by using a different angle. And this is what your lab is going to go into. You're going to launch at different angles and see which angles will produce the same distance. And as you can see here in this diagram, you can probably look it up online, and there are all the answers. Okay. All of your angles need to add up to 90 in order for it to be the same displacement. Okay. So if I have 75, as you see here, okay, that's going to be the same as 15. Notice 75 plus 15 is going to give you 90. Here I have 60 plus 30. That gives me 90. They give me the same displacement. Notice 45 right here is the maximum displacement. So if you want the maximum range of a projectile, whether you're throwing it or shooting it, you want to make sure that it's at a 45-degree angle. Keep in mind, though, that this is without air resistance. So if you have air resistance, it's going to be a little bit different. Okay, so again, the maximum range is about 45 degrees. For a baseball with air resistance, you're going to have to be between 25 and 34 degrees. Okay, so that's kind of weird. You would think that you would get a better range the higher you hit it. But remember that if you go this way, it comes down, right? If you shoot this way, it goes up more and then comes down. So you want to keep that baseball between 25 and 34 degrees coming off of the bat in order for you to get the maximum range or to get that home run. The other thing that helps is that they throw it fast. So if you can hit a fastball, then you're going to get a lot more momentum, right? The impulse is going to be much, much larger. And then you can increase the force by decreasing the time of contact. So hitting it harder decreases the time, increases the force for the same impulse. So when it comes to baseball, though, there's a lot more to it. As you can see from here, just hitting the ball without air is fine, but we have air. And they move very fast, so they're going to have air resistance. And then the temperature of the air also affects it. So what we're finding is that as we increase the temperature, we're getting balls that are traveling much farther. With a golf ball, you have to hit it around a 38-degree angle due to the air resistance. Also, there's dimples on the ball, and that also helps with having that ball move a specific way. Okay, so without air resistance, the time for a projectile to reach its maximum height is the same time as it takes for it to return back to ground level. Okay, so a cannon shoots a ball into the air at a speed of about 40 meters per second. It rises and then it falls back down to the ground. And again, that will be a parabolic curve. As it rises to the top, the speed will decrease by 10 meters per second every second. As it falls, it's going to increase its speed by 10 meters per second every second. The speed of the descent is going to be the same as the speed of the ascent based on the same height, as you can see here. 10, 10, 20, 20, 30, 30, 40, 40. The only difference is going to be the direction. Okay, and this is for a reaching its maximum height. Okay, it's time to check with your neighbor or check your understanding. The velocity of a projectile has horizontal and vertical components, assuming negligible air resistance. That means ignore air. The horizontal velocity component of a projectile, A, increases with time, B, decreases with time, C, remains the same, D, not enough information. Okay, let's see if you have the correct answer. The correct answer is C. It remains the same. Great job, everybody. Okay, when no air resistance acts on a fast moving baseball, its acceleration is A, downward, B, tangential, C, centrifugal, D, centripetal. Okay, there's no air resistance. Which direction is the acceleration? Okay, let's check your answers. The correct answer is A. The acceleration down is constant. It's the acceleration due to the Earth, which is negative 10 meters per second per second. Okay, if we neglect air drag, a ball tossed at an angle of 30 degrees above the horizontal will travel the same distance as a ball tossed at the same speed at what angle above the horizontal? This is a 30-degree. Will it be 45, 60, 75, or none of the above? Okay, let's check your answers. The correct answer is 60. Very good. Everybody got that. So 30 plus 60 gives you a 90-degree angle. Very good. You remembered it. Okay, so now we're going to talk about satellites. A satellite is a projectile, believe it or not. Satellite motion is just a high speed projectile. So imagine this. I have a ball that I launch at an angle, okay? And it just has a certain speed. It'll go up and come back down. Now, I launch it at a faster speed. What happens? It goes up higher and then falls back down. I make it even faster. What happens? Goes up even higher and comes back down. Eventually, you're going to get to the point where you're going to launch it so fast that it's actually going to fall around the Earth instead of into the Earth. And that's exactly what satellite motion is. We make it go so fast horizontally that as it falls due to gravity, it's going to fall here, then around. And it'll just keep falling around the Earth. Okay. So a satellite is just simply a projectile that's being launched at such a speed that it keeps going and falling around the Earth indefinitely. So let's check your understanding. A girl throws a rock horizontally from a cliff. 1 second after she releases the rock, it will have fallen vertically by, is it 1 meter, 5 meters, 10 meters, or none of the above? Give you a hint, it's in the picture. Okay, let's check our answers. The answer is B, 5 meters. Regardless of the initial horizontal speed, the ball will fall 5 meters for every second due to the earth pulling it down. So the first second it falls 5 meters. The second, it falls 20 meters. The third second, it's fallen 45 meters. Okay, so there's two ways that you can get a satellite into an orbit. The orbit can be what we call a circular orbit, or it can be what we call an elliptical orbit. So we're going to talk about circular orbits first. The first thing we're going to talk about is the speed. The speed must be great enough to ensure that the falling distance matches the curvature of the Earth. Okay, so if you do not have the distance to match the curvature of the Earth, it's going to fall into the Earth, or it's not going to be in orbit. It'll have a shape that will allow it to escape the Earth's gravitational pull, and it will go off into space. So sometimes we launch rockets and they don't quite make it to apogee, and they fall back down to the Earth. This is typically why we launch a lot of rockets over the ocean, just in case that happens. So that if something does go wrong and it doesn't make apogee, it'll fall into the ocean, and then we can try and retrieve it. The other thing is that we make it so that it goes right around the Earth and becomes a satellite. So we have a lot of Starlink satellites for internet and GPS satellites to help us find our location. The other thing is that you can launch it with fast enough speed that it escapes the surface of the Earth and then travels out of our gravitational pull. So this is what we would have to do with the Orion capsule in order to get people to the moon again. This is also what we do when we send probes to other planets, or when we start sending them to, like recently, we've been sending them to asteroids, collecting samples, comets, collecting samples, moons, collecting samples. So there's a lot of times that we have to send things and not put them in orbit. Okay, so here is something to give you some idea about positioning. Let's talk about the GPS satellites. GPS satellites have an altitude of about 12,540 miles. Oops, sorry, I hit the wrong key on my keyboard. And that puts it well above the atmosphere. That means there's no atmospheric drag on them. And that allows them to not need bursts of energy or thrusts in order to keep them in orbit. Okay, you want your GPS satellites to always stay in the same position, or either whether it be geosynchronous orbit or in an orbit that's always going to stay the same way. It doesn't decrease in time, doesn't decrease or increase in height. The ISS, though, is about 350 kilometers above the surface, or about 260 miles. Okay. This puts it in the upper atmosphere of the Earth. It's very, very thin, that's true, but there's still particles in that region that can cause the ISS to slow down. And because of that drag, there are periodic boosts that they have to give the ISS in order to keep it in orbit. And so eventually that's going to stop, and we're not going to do that anymore. And we're hoping that it will crash in a place that we want it to crash. Or it could be that we start bringing down the pieces, or it could be that we move those pieces closer to the moon in order to make the pathway gate, which will then be used to take astronauts from the moon base to Mars. At least that's the goal. That's pretty exciting. All of this part just makes me feel all warm and fuzzy, because this is us getting to that point where those Star Trek movies are not going to be, sci-fi, science fiction. It's going to be science reality. And I'm very excited for that. A lot of people think, Well, why are we spending all that money on space when we could be feeding the poor or the hungry? Um, and that's true. But look at it this way: all of the research we do in making freeze dried food for astronauts to keep it, to make it last long, same thing with dehydrating things, same thing with protecting foods. All of that has helped us with our own food sources. So, for instance, making crops less susceptible to pests and insects, a lot of that research comes from NASA in trying to make sure that we can have crops that can grow in space. Some of the other things, genetically modified crops, hydroponics is huge. And that came about from the space program. So freeze dried foods, uh, all of that stuff comes from the space program. So it's really amazing. Even our computer systems, Velcro, um, fire prevention, uh, the foams that they've developed in the space program have helped us put out fires. Insulation for the spacecrafts have helped us to make fiberglass insulation for homes now. Smoke detectors came from the space program. They needed to make sure that if there were a fire on board, that the astronauts would be able to escape in a timely manner, just from the smoke. So, yeah. Oh, power tools. They came from the space program. So there's so many technologies that we have that we don't even realize wouldn't be here or wouldn't exist if we didn't put that money into the space program to explore. So every little bit that we put in, we get back tenfold, I believe. All right, I'm off my soapbox. Okay, so how do we describe the motion of a satellite? The motion is directed perpendicular to the force of gravity. So here's your Earth. This is the direction of motion. This is the direction of the force of gravity. This is the direction of force of gravity. This is the direction of motion. So notice that if I do this, this is the direction of motion. This is the gravity. Notice that as I go around, they're always perpendicular to one another, making a 90-degree angle. Okay. So because of that and the location of the orbits, you have different speeds. So for instance, the closer you are to a planet, the faster you're going to go. So notice the ISS, which is very close, is only going to take 90 minutes to go around the Earth. So every hour and a half, you should be able to see the ISS above you if its trajectory is crossing your state or your location. If you're looking at the GPS satellites, they take 12 hours. Our moon takes about 27.6 days. So notice how much further away it is from us. Here you can see a better idea of the curvature of Earth. Notice that for a 5-meter drop, it happens every 8,000 tangential kilometers. So if you measure a line that's at 8,000 tangent to the surface, you can drop 5 meters, and that shows you the curvature. You can also find the curvature by looking at different locations at noon. And you can see that the shadow that is made can also tell you the curvature of the Earth. So a lot of people say, oh, we can't prove that it's round unless you go to space. And that's not true. If I look at a stick at noon at my location and then somebody up north looks at their stick at noon, they're going to have a shadow and I'm not. Or I'll have a slight shadow, they'll have more of a shadow, and that shows you the curvature. Okay, so check with your neighbor and type into the chat. When you toss a projectile sideways, it curves as it falls. It will be an Earth satellite if the curvature it follows, A, matches the curved surface of the Earth, B, results in a straight line, C, spirals out indefinitely, D, none of the above. Okay, remember we want it to be a satellite, so it has to match the curvature of the Earth. So the answer is A. For an 8 kilometer tangent, remember the curvature is down 5 meters. So every projectile near the Earth's surface falls 5 meters every second. The projectile travels horizontally. So that is following that curvature of the Earth. Okay, when a satellite travels at a constant speed, the shape of that path is A, a circle, B, an ellipse, C, a parabola, D, a hyperbola. A satellite travels at a constant speed. What's the shape of its path? The satellite's path when it doesn't ever hit the ground. Okay, let's check our answers. The correct answer is A. Very good, everybody. It's a circular path. Um, let's see. I want us to go ahead and take a 5 minute break now because this is really heavy duty stuff. And I'm doing a lot of talking, and there's not a lot of interacting taking place right now. And it's not you, it's the lecture. So let's take a break right now. Let's come back at 6:55, and that way we can get out of here even sooner. So 6:55, we're going to come back and finish this up. I do have some more interactive stuff later on in the lecture versus right now. that's different. There we go. Okay. I want to get us out of here early so I can go over some things with those of you that need a little help. So let's go ahead and get started again. Okay, so we just got done talking a little bit about the circular orbits. Again, when we're launching things into space, so for instance, the payload in the orbit, it requires us to have control over specific things. One, we need to be able to control the direction of the rocket. Okay, so initially when a rocket is fired, it's vertical. Okay, and so I'm not sure if any of you have ever seen a launch. Sometimes, if you're close to the coast, I think Elizabeth City is close enough. If you look towards the not towards the water for the Outer Banks, but if you were to look straight up towards the Chesapeake Bay, which you won't see, but if you look north during a launch at Wallops Flight Facility, you could probably see it. And what you'll see is you'll see the rocket go straight up, and then all of a sudden it starts to tip and goes almost horizontal. Okay. So what's happening is that once it gets above the atmosphere, it then starts to move horizontally because you need to get it fast enough in order to fall around the planet instead of into the planet. As you can see from this diagram here. Notice here, rocket launches straight up. It's not going fast enough, and you have it go horizontal, and then what happens? It falls right into the earth. Whereas here, notice that you get it up and you're going fast enough now that it will actually fall around the earth instead of into the earth. Okay. So one, the direction of the rocket is important, but also two, how fast you're going will also determine whether you stay in orbit or not. Okay, so the final thrust to orbit speed of 8 kilometers per second will have it fall around the Earth instead of into the Earth. Now, this sounds very simple the way it is, right? It's a lot more complicated than that. And I don't know if you've ever watched the movie Hidden Figures. If you haven't, you might want to give it a try. I know that there's quite a few things in there that are poetic license as far as the accuracy is concerned, but you can easily look those things up. But the calculations were not. And so to do these calculations by hand or by a computer machine, which is basically like a big giant calculator, was pretty incredible. Okay, so now we're going to talk about elliptical orbits. All of our planets travel in an elliptical path. None of them travel a circular path. So it's kind of important for us to talk about elliptical orbits as well, because the planets travel them. A projectile just above the atmosphere will follow an elliptical path if it's given a horizontal speed greater than 8 kilometers per second. Okay, so 8 kilometers per second gives you a circular orbit. If you go a little bit more than that, it's going to give you an elliptical orbit. Okay, so a generic orbital path is an ellipse. Okay, so all the planets, like I said, travel elliptical paths. An ellipse is a special kind of oval. It can be formed by, as you can see in the diagram, you take two pins and you mark them a certain distance apart, put a string that goes around those pins and draw along that line. It's sort of like one of those, I don't know if anyone knows the spirographs or Etch-a-Sketch kind of thing. A spirograph is the one that goes like this. And what it does is it will draw that elliptical shape for you. So what's happening is these two pins that you see right here, and right here are acting as the foci points. And then as you draw this, it goes around those pins, this piece right here, and it draws your ellipse. Okay. Now, a circle is actually a special kind of ellipse. It's where you take these two pins and you put them together at the same spot in the middle. So there can't be any space between the two pins. You have to put one right on top of the other. And now you have the string attached to one pin. And now it goes around and makes a circle instead of an ellipse where you have two pins. Okay. So the speed of the orbiting satellite in an elliptical orbit will change. And that's because the gravitational force will change. Remember, when you're going around the Earth, the only thing acting on you is the Earth, right? There's no air resistance. There's no other forces acting on you. It's only the Earth. But when you travel a circular path, that's okay. You're the same distance from the center. And that means that your gravity is the same in that orbit. Okay. But what if you're traveling an elliptical path? So here you're farther away. And remember, we talked about this in the lab. So mass is the same, right? I'm not changing the mass, I'm just changing the distance. What happens? It's a 1/d² relationship, right? So the farther away I am, the much less force I'm going to have. Okay. Now I come around here and I get closer to the Earth. There we go. Now the distance is less. So what happens to the force? It becomes more. Okay. Now I'm going around the Earth again. I can't do it that way. I'm going to go around the Earth again. Now I'm moving further away. What happens? My distance increases, and therefore my force decreases by 1 over the distance squared. So as you move closer to the Earth, your force will increase. As you move away from the Earth, the force decreases. Less force means less acceleration. Less acceleration means your velocity does not speed up as much. Okay. And so what happens is as you're moving towards the sun, you're increasing your acceleration, therefore you're increasing your velocity. As you move away from the sun, and I'm talking about planets going around the sun, as you go towards the sun, you're increasing your velocity. As you move away from the sun, you're decreasing your velocity. And so, believe it or not, we are closest to the sun in the middle of December. We are farthest from the sun in the middle of July. So a lot of times people think, oh, how far away we are determines our seasons. No, our seasons are actually controlled by the tilt of the Earth, not how far away it is. Because again, we're farthest from the Earth or the sun when we are at in July, and we're closest to the sun when we're in December, January. Okay, so if you see here from these 3 points, here, as you're close and you start moving away, you're going to lose some speed. As you get all the way out here, you're going to go slower and slower. Once you move to here, you're going to start getting more gravity. So you're going to speed up. You're going to pass by here the fastest, and then you're going to start slowing down. Then you're going to start speeding up, and then you're going to start slowing down. So elliptical orbits can be helpful if you're trying to look at a certain place on the Earth really close, and then the other part of the time you don't really care. Typically for us, the Earth's eccentricity, or how elliptical it is, we're real close to a circular orbit. Pluto has a very elliptical orbit. So when we say elliptical orbits for satellites, we're not talking about much of a difference between its apogee and its perigee. And I'll mention those two words later on when we get more detail into this. Okay, so let's check your understanding. The speed of a satellite is in an elliptical orbit is A, greatest farthest from the Earth, B, the least when it's farthest from the Earth, C, remains constant for all elliptical orbits. D, is greatest if the orbit is circular. Okay, let's check your answers. B, when it's farthest, it's going to be the least amount. Okay. So a satellite, again, in an elliptical orbit, half the time recedes from the Earth and loses speed, and half the time approaches the Earth and gains speed. Okay, here is a picture that shows the difference between circular and elliptical orbits. Okay, so notice here that your energy, okay, right here and here and here and here, they're all the same, aren't they? Okay. So, and that's because you're traveling the same speed all the way around. You're the same height, no matter where you are. Potential energy, remember, is mgh. Depends on the height. Your kinetic energy is 1/2 mv squared. Depends on the speed. Okay. If you don't change your speed, your kinetic energy doesn't change. If you don't change your height, your potential energy doesn't change. If I add PE and KE, the potential energy and the kinetic energy, potential energy and kinetic energy, it has to equal the same amount no matter where I am on the orbit. That's energy conservation. Okay, now look at your elliptical orbit here. Okay, notice here the force changes. So here it's stronger than here. This is where it's the weakest, but the farthest away, right? So what's going to happen? Speed is going to be the least. Height or distance is going to be the most. I'm going to have mostly potential energy here and a little bit of kinetic energy. As I start to move in, I get closer, so I'm decreasing my potential energy, but I'm also getting faster, which means I'm increasing my kinetic energy by the same amount. Okay. Now I'm even closer. My potential energy gets decreased. I have to go faster in order for them both to be equal to the same amount as here. Okay. So energy conservation helps us explain why an elliptical orbit allows us to get faster here and slower here. It's because the energy here has to be the same as the energy here. Okay. More potential, less kinetic, mostly kinetic, very little potential. Okay. So these two positions, they kind of swap. Oh, well, what happened there? Oh, I went the wrong way, I guess. Okay, so let's talk about Kepler's laws. Basically, what this says is yada, 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 blah, 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 blah. So I'm going to tell you a story. You can fill in the blanks, and I'm going to tell you a story about Tycho Brahe and Johann Kepler. Tycho Brahe was around 1600, and he was a Danish nobleman. Some people pronounce his name Brahe. I was always taught bra, like the undergarment bra. Tycho borrowed money from the king and built the very first observatory. Bought extremely expensive, well-made devices and instruments in order to measure the exact location, altitude, and azimuth of stars and planets. And so he collected data over several years. He then hired Johann Kepler to use the data to prove the geocentric model. Okay, the geocentric model is the Earth-centered model. Everyone at that time was starting to find evidence or be dissuaded that the geocentric model was the right model. You start to hear more murmurings about how we are probably going around the sun instead of everything going around the earth. And so Tycho was not stupid. Okay. It wasn't like he was just like, oh, I'm just going to say it's this because I want to believe everybody else. He actually had a reason for stating that the geocentric model was correct. And that's that if this is the Earth and it's going around the sun, okay, then when you're looking at planets, when you're here and looking at the planets that way, okay, you're a certain distance away, right? Then when I move to here, I'm at a different location. I would see it, the background shift, right? Here's the star. Here's the Earth, looking at it. Now I'm here. Now look at it. It's shifted, okay? If I'm here, it's shifted. If I'm here, it's shifted. Okay, notice the way I'm pointing. That's called parallax. And I'm going to show you an example. I want you all to do this right now. Those of you that are still awake and paying attention, not handing out candy, although I would hand out candy too. I want you to take your finger and I want you to close one eye like this. And I want you to take your finger and line, I'm going to use this one because it's over here, and line it up with something behind you, like really far away, not behind you, sorry, in front of you, really far away. Okay. Now what I want you to do is I want you to look at that object with just the other eye and go from one to the other. Here, this is what I'm doing. I don't know, you might not see my finger. What you notice is that the background shifts. That's called parallax. Tycho Brahe did not see parallax when he was looking at the planets from different positions. Okay. And because of that, he said, we can't be going around the sun if there's no parallax, right? Because if we are going around the sun, then we would see this shift due to the different locations. Here's the sun. Here's the moon. Here's the moon, or here's the Earth. Here's the Earth 6 months later. We see the shift with our own eyes. You should see the shift of the planets, which he didn't. Okay. So he goes and hires Johann Kepler to analyze the data and show that it proves the geocentric model. So Kepler starts analyzing the data. Tycho had some issues in life. Okay. This is a little segue, your little brain break, but it's very interesting and it might end up being an extra credit question on the test. So you want to pay attention. All right. So Tycho Brahe, when he was in his youth, had a duel. And basically the duel was to prove your honor. Well, he didn't really win the duel. He actually got his nose sliced off. So if you look at pictures of Tycho Brahe, you'll see that it looks like he has a Band-Aid on his nose. It's not a Band-Aid. It's actually a piece of wax. And then he also had a metal plate that he would put over his nose. If you also look at his picture, he's not a very handsome man. So that led to excess drinking. And what happens when you drink a lot? You don't make good decisions, right? So he ended up frequenting a lot of ladies of the evening, and he ended up contracting syphilis. So now there's another reason to drink. One, I got a metal nose. Two, I have syphilis. At that time, remember, no treatment, very painful, not fun. Okay, so he ends up developing liver cirrhosis. He ends up having syphilis, which is nasty. And then he goes to a banquet with the king. And the thing is that when you sit at a banquet at the king's table, you can't get up until the king does. And so if you have to use the latrine, you have to hold it. Well, Tycho held it very long and he ended up getting urinary tract infection. He ended up dying several days later. At first, we thought it might have been the liver cirrhosis or the syphilis Turns out that it was a urinary tract infection that took him out. So here's the moral of the story. Don't have a duel. There you go. That's it. Or duck. Don't lose your nose. So when Tycho died, and it was only a year after he hired Johann Kepler, Johann was really interested in this data, and he was making some headway with it. And so after several years, he was able to come up with his first two laws. It took him 10 years to come up with the third law. And when I show you that third law, you're going to say, yeah, of course it took 10 years. I would have never figured it out, by the way. So Kepler holds on to the data. Tycho's family wants the data and all the tools from the observatory. They're all part of Tycho's estate. Johann Kepler says, no, I'm not giving you the data. So what happens is the family takes Kepler to court, and Kepler loses. He's got to turn over all the data. He just moves. He keeps moving. So the family keeps coming after him for the data, and he just keeps up and moving and never gives it back. Thus, the reason he has it for 10 years and is able to come up with the third law of planetary motion. So there you are. There's a little story. There's also rumor that that Kepler, Johann Kepler, was a little bit of a mystic as well. And rumor has it that he would actually, on like the solstices and he would dance around with candles naked in order to get inspiration. I don't know if it's true or not. That's just the rumor. So there you go. There's your little segue about two very important people in the world of astronomy. So let's go back and talk about what those laws are. Did I miss the first and second law? Oh, my Lord. Okay, these might be out of order. I don't know. Yeah, they've got to be out of order. Okay, so this is the third law. And basically what he found was that, let me see if I can find the other one. Here it is. They're out of order. Okay, so this is the next information that you should have in your slides. So the first law states that planets travel elliptical paths with the sun at one focal point. This is where we get into the elliptical orbits. Okay, so how did Tycho figure this out? Well, he saw that the planets that are going around the Earth are not moving the same amount in the sky. There's certain places where they're moving more and certain places where they're moving less. And that's how he figured out that the speed had to be changing. And if the speed was changing of these planets, then that meant that they had to be traveling elliptical paths instead of linear paths or straight paths or circular paths. And if you were to actually take circular graph paper and actually plot out the location of Mars over a long period of time, you would actually see that it forms a slightly elliptical path. So quite ingenious. The second law is that the planet will sweep out equal areas in equal amounts of time. And what that means is that the planet will move faster the closer it is to the sun. It'll move slower the farther away it is from the sun. And so let me show you that. Let's see if I should be able to click on this. Let's see. Nope, that's an eraser. I need to get rid of this whole thing here. Let's see if I can make this work. Nope. Oh, there we go. Okay. All right, I'm just going to show you the picture. The videos aren't working for some reason in this lesson. So notice here that it moves from here to here in some time period t. Okay, notice it moves from here to here in that same amount of time. Then it moves from here to here in that same amount of time. Notice here, it only moves this little bit in the same amount of time. It has to be going slower, right? If I put beans in this part here, and then took those beans and put them in here, I would use the same exact number of beans in order to cover this area as I would this area. And that means that the areas are going to be the same. Newton actually developed calculus to actually prove this. And so, in order to do that, you had to find the area of these slices, which is very complicated. So, he figured out that if you took these slices here and you made them very, very small and you made them into little rectangles and then added up all those rectangles, that you could actually get the area of this piece right here. So basically, you would be taking thin lines from the center out all the way around and then add up the area of each one of those lines, add them all up together, you would get the area of this piece right here. So that's what calculus does. It makes it a lot easier for you to calculate the area instead of putting a bunch of beans in there. Okay, so hopefully you'll remember some energy conservation, a satellite motion, objects. Oh, let me go back. Sorry, I didn't get the third law for you. Here you go. Basically, this took him, again, 10 years to come up with. The period squared of a planet is equal to the mean distance to the sun cubed. Now, very, very complicated, right? It's basically p squared equals a cubed, where a is the mean distance from the sun to the planet, and p is the period, the time it takes to go around the Earth. So the Earth has a mean distance of 1 astronomical unit, and it takes 1 year to go around. So if you look at the relationship, 1 squared equals 1 cubed, it works, okay? And so if you look at this graph, what they're showing you here, right here, is they've calculated this is the period squared. This is the mean distance cubed for all the planets. They plotted them, and look what happens. They make a straight line. How is this important? It's important because now we can figure out from this relationship the mass of every planet by knowing how long it takes to go around the sun and by knowing how far away it is. We can also figure out the ratio between one planet and another. Okay. We can also figure out the period or the mean distance or the mass of a planet based on how its moons move around it. Final thing, we can find planets like the Earth in other solar systems in our galaxy by looking at Kepler's third law. So the most exciting thing about this is that by using Kepler's third law and looking at a star, we can predict where a planet would be located based on this law and look in that location to see if we find a planet. And that's how we found thousands of exoplanets. We have found thousands.
I don't have an answer for that.
Oh, that was Alexa. Sorry. We found thousands of planets by using Kepler's third law. Okay, so objects moving will have kinetic energy, right? Objects that have a certain height above the Earth's surface will have potential energy. Okay. Satellites in orbit will be moving, so they have kinetic energy. They'll also be a height above the surface, which gives them potential energy. The kinetic energy plus the potential energy must be the same for every point on the orbit. Okay, so that's something we've already covered. I'm going to let you go ahead and fill that in. So This allows us again to trade off speed with distance. So the farther away you are, the slower you go. The closer you are, the faster you go. If I'm going faster, the closer I am, I'm going to be sweeping out more area in the same amount of time as I would if I were further away and sweeping out that area. So, this energy conservation leads us to Kepler's second law, which is sweeping out equal areas in equal amounts of time. It has to happen that way in order for energy to be conserved. Okay, so in a circular orbit, we've already covered this. Your potential energy and your kinetic energy and the speed are going to be the same for a circular orbit. Okay, so again, potential energy plus kinetic energy will be a constant. It will be the same. The force doesn't change because you're the same distance away. And therefore, your speed won't change because you're not changing how close or how far away you are from the planet. This is a fairly normal type of orbit. But when it comes to satellites that are used for measuring climate change, we tend to have polar orbits, which have to be elliptical. And the reason for that is that our planet is not completely a sphere. Due to its rotation, the poles actually move in a little bit, and we call that oblateness. Gas giants are even worse. Like their radius is so much different than from pole to pole. For us, pole to pole is slightly less than from the equator to straight across. Okay. So ours kind of looks like a pumpkin, almost a round pumpkin, but slightly squished on the top and the bottom. Okay. So, with that being the case, if we're going around the equator, we're going to be the same distance. But if we're going pole to pole, notice that it's going to change because you have to go out further here than you do from pole to pole here. So your orbit is going to look more elliptical this way. Okay. So polar orbits is what we typically use. We typically look at maybe a 12 to 17 degree tilt of that orbit in order to sweep out the most area across the world for our climate measurements. So the satellites that do that kind of stuff are collecting information about CO2. They're collecting information about oxygen. They're looking at water vapor. They're looking at radar to look at canopy height. They're also using infrared in order to look at plant life versus non-plant life. And so there's a lot of things that satellites can measure from that polar orbit. For elliptical orbits, we've already talked about this before. Potential energy will be greatest at what we call apogee. I always think of apogee as being away. Apogee, away. They both start with A. And I look at perigee as nothing. I got nothing. But I just know apogee means away because they start with A. Perigee is going to be your closest point. If you're looking at the actual orbit itself, the apogee would also be called the aphelion, and the perigee would be the perihelion. And that just means the same thing. Helion just means around the sun. So when you're talking about satellites, it'll be apogee and perigee. When you're talking about the sun, it'll be aphelion and perihelion, which helium means sun. So again, right here and right here, PE and KE will be the same. Here, mostly KE, very little PE. Here, you'll have mostly PE, very little KE. Okay, so the satellite will gain altitude and move against the gravitational force. Its speed and kinetic energy will continue to decrease. until it reaches apogee, the farthest point. Once it reaches apogee, it's sort of like that baseball coming back down. It starts speeding up again. Okay. So after it passes the apogee, the gravitational force is going to start increasing. The velocity is going to start increasing. That means you're going to have more kinetic energy, and that means that you're going to have more speed. Okay. So the speed of the satellite will increase as it goes to perigee. And then again, this cycle keeps repeating itself. So let's talk about escape velocity. How do we get it out of the gravitational pull of the Earth in order to get it to orbit? The first probe to ever reach the escape velocity is going to be Pioneer 10, and that was in 1972. So actually, I'm sorry, that was the first one to escape the solar system. It was launched in 1972. We also have the Voyager probes, Voyager 1 and Voyager 2. They're actually still collecting data. And they were launched slightly after this. Pioneer 10 and 11 were the first two to reach the through the asteroid belt. And then Voyager 1 and Voyager 2 went after that. Voyager 1 and Voyager 2 also had information on there about different languages. In fact, what's funny is the disc, the gold disc that they made and put on the Voyagers, has languages spoken that are no longer spoken. They're extinct languages now that are on that probe. So Pioneer 10 and 11 went to visit Jupiter and then also Saturn. Okay, here we go. By the way, this is the 45th slide out of 47. You only have 2 more to go after this, really 1 more. When a projectile achieves escape speed from Earth, it, A, forever leaves Earth's gravitational field, B, outruns the influence of Earth's gravity but is never beyond it, C, comes to an eventual stop, returning to Earth at some point, some future time, D, reaches a maximum height and then enters a perpetual orbit. Okay. I know you're all waiting for one person to answer, aren't you? I'd be like, oh, I don't want to type the first one. I don't want to be the first one. What if I'm wrong? Yep, I was that kid. Okay, let's check your answers. B, you outrun the influence of Earth's gravity, but you never get beyond it. Let me tell you a little bit about that, because a lot of times we think of people being weightless in space, and that means there's no gravity. That's not true. Remember, the International Space Station is falling into the Earth. It's in free fall. So here I am in free fall, falling straight to the Earth, but I'm also moving horizontally. So I'm moving fast enough horizontally that instead of falling into the Earth, I fall around the Earth. If I'm in free fall, that means I have gravity. The gravitational pull at the International Space Station is about 8.6 meters per second per second. Okay. 10 on the Earth's surface at sea level. We're really rounding that up. 8.6 is more than on the moon. Yeah. Okay. So why is it they float around? It's because they are also falling with the spaceship. So if I'm falling at the same rate as the spaceship, then I appear to be weightless, right? The normal force is 0. That's what your effective weight is. Is their weight actually 0? No. It's their mass times the acceleration due to gravity, mg. Okay. So yes, that has changed, but why is it appeared as be 0? There's no normal force, which is how you measure that force. Okay, last thing. Voyages to the moon, Mars, and beyond begin with launches that exceed that escape speed from Earth. So that's what we need to work on. We need to get past that uh, escape speed in order to send humans out into the solar system and eventually send them out into the galaxy. So that ends the presentation of the lecture notes for tonight. I'm going to go over the lab work that's going to be due next week. For those of you that have gotten a little bit behind, and there's quite a few of you, I've been grading, and there's quite a few of you that have a lot of zeros in the grade book. You really need to get that up. If you are unable to get this work done due to technology, please contact me. If it's that you don't understand something, please contact me. Okay, I'm here to help you. This is a difficult platform for a physics class. I understand that. Teaching physics online is not my number one thing. I would prefer face to face because then I can show you demos. We can actually throw things around the room. Doing it virtually is very difficult. So I understand that you may not know what you're doing. So please, please, please contact me, email me, text me. I will hopefully get back to you. And if what I tell you doesn't help you, come and see me at office hours. Okay. I have some favorite people that come and see me every week in office hours. Thank you very much. I love you. Uh, and I'm willing to help you. Okay. If you also have gotten so far behind that you don't think you can get caught up, you need to tell me. Okay. Just a reminder, the drop deadline for this course is coming up shortly, and I want to make sure that you don't have to drop. Okay. So start getting that work done. If you don't understand something, please see me. Okay. Does anyone have any questions before we go? Okay. I'm going to quickly go over the lab for those of you that are interested. And for those of you that aren't, you are free to go. Oh, you gotta be kidding me. Here we go. Open. Download. Okay. I'm gonna move my paperwork. Oh, I don't know what is that? Okay. So here is the lab you're gonna be doing. The reason I want to go over this with everyone is because I wrote it. And that means that I need to make sure that you understand what I need you to do. So there's certain things you're going to do. You're going to change the angle of your projectile. You're going to see which angles have the same uh, distance or the same range. That's what range means, the same distance traveled horizontally. And then you're going to change the initial speed. So what is a projectile? A projectile is an object that's launched. That's basically it. So you can use a ping pong ball. You can use, don't use anything really heavy. I'm not so sure a small foam ball is going to be okay unless you're using a small rubber band or a medium sized rubber band. You want something that's fairly long, but not real stiff. Okay. So thick rubber bands may not be good. One thing you could do, I don't know if you've ever done this as a kid, cut a rubber band in half, staple one end to one stick, end of a stick, and the other end to the other stick, or tape it on there, or whatever, and then you have yourself a slingshot. So that's basically all you're going to do is you're going to build yourself a slingshot. I've done it with my fingers. Um, Maybe these two fingers because you have some space to put the paper ball between it. Um, if you want to do this with instead of rubber bands, um, this is tricky. I know that my sons used to build those paper footballs, right? And they hold it like this, and then you flick it with your finger. The problem is that when it comes to the part where you have to increase the speed, you got to increase the flick, and you have to be consistent. And I'm not so sure that that would work. But if you can get it to that point, like if you've played a lot of paper football games, then by all means do that. You do not want to launch this all the way across a room. If you have a desk, you want to be able to launch it from in front of you to maybe 5 or 6 inches, all the way to maybe 20 inches at most. Okay, so you don't want anything crazy. Um, if you want to build something really big and do this, by all means do so. I'm not going to stop you from doing that, but you don't need to. Okay, you can just do this with, here's some examples. We have a rubber band catapult. You use cardboard base with rubber bands attached to it in order to launch a ball. Some launchers have popsicle sticks. If you have a spoon, I wouldn't recommend a metal spoon, but a plastic spoon kind of works good. So you take the spoon and you put the end on the table and you put the ball in the spoon and then you pull it down a little and flip it. Toilet paper tube launcher, that's actually kind of cool. What you do is you cut it in half and then you put slits at the end, put your rubber band there, and then it's in the tube and you pull the rubber band back and let it go and it shoots it out. Nerf guns. If you've got a Nerf gun, use it. Okay. Anything that can launch something and you can change the speed. I'm not sure you can. I think my son had one where you could pull it multiple times in order to get it to fly farther away. Another one, my son, I got him this for Christmas one year. It's just a little PVC pipe, and you use those little tiny colored marshmallows. You put it in there, and you can blow it. Just give it a quick puff, and then you do harder puffs and harder puffs to at the same angle for the further one. Okay, so you just need something that can launch something else. That's all you need. You will need a ruler. You may need a protractor. Again, you can kind of figure out, like if you take this and divide it in half, that's 45 degrees. Divide this in half, that's 30 degrees. Divide this in half, that's 60 degrees. So you don't even need a protractor. You can just do these marks on a piece of paper and hold it up to it to make sure you have the right launch angle. Okay, so the first thing you're going to do is you're going to launch your made up ball, whether it be a marshmallow ball, a ping pong ball, at a 30-degree angle, and you're going to record how far it goes. Okay, you're going to do that 3 times. Now, one of the big things that students do is they say that 3.5, 4.2, and 3.1 are not the same number. And therefore, I did not prove what I needed to prove. When I say the same number, we're talking about 3.5 versus 15. That is not the same number. If you're getting 3, 4, 3, 4, 5, 4, that's okay. But if you're getting 2, 5, 6, that's not okay. That 2 is not in that range. Okay. So you want 3 numbers that are fairly close to one another. They don't have to be exactly the same. Okay. So this I would consider experimental error. You're good. Okay. Here's the table. You're going to do it for 30 degrees. Should be degrees. Yours is not going to say degrees. You'll have to fix it. Okay, 30 degrees, one launch, two launches, three launches. Get your numbers as close as possible. And then you're going to find the average. Add them together, divide by 3, put it in here. Then you do it for a 45-degree angle. Same thing. Then you do it for a 60-degree angle. Same thing. Which angle produced the largest distance? If you say 60 degrees, we know from the lecture notes that that is not correct. So if this comes out larger than this, you did something different. Okay, you didn't stretch it the same amount. You were wiggling around with the angles. The numbers are too different, or maybe this one had a really high one and two really low ones. There's probably some error in there. So you may have to redo this to get these numbers to be larger than these. Does this match what you learned in class? The answer should be yes. A 45-degree angle should give me the maximum displacement or maximum range. Did any of these angles give you the same distance? Do any of these add up to give you 90? Yes. So you need to figure out which two add together to give you 90. And those numbers should be close. If I get 3.5 for one of them and 3.5 and 3.9, that's close enough. If you get 3.5 and 7.2, that's not close. And then you did something wrong. Okay. I want to explain something about physics and science. It's okay to get the wrong answer as long as you understand that you're wrong. Okay. All you got to do is say, it should be a 45-degree angle, but it isn't. I think I was pulling on the rubber band too hard for the 60-degree angle and not hard enough on the 45-degree angle, and that's why they're different. Okay? Just explain what you think you did wrong or what you think is different, and that will help you to for me to say, oh, okay, they didn't get it right, but they know why, that they should have gotten this answer, but they didn't. Okay. So you should have two angles that add up to give you 90 degrees, and they should be close. And if they're not close, you need to figure out why they're not close. Well, maybe it wasn't exactly a 30-degree angle or a 60-degree angle. Well, maybe I was pulling too much and not enough on the other one. There's got to be something going on. There's also, if you don't even want to do this, there's simulations out there. Just text me and I'll send you the simulation. For part 2, you're going to do exactly the same experiment, only now you're going to stretch the rubber band 1 centimeter, then 2, then 3. 3 trials, average them together. What kind of relationship do you see between the stretch and the distance? Should be linear. And does this make sense? Yes. Yes, it does. All right. So thank you all for staying with me until 7:50. Because you now have all the answers to the lab questions. Yay. Okay, does anyone have any questions about the lab? Okay. Does anyone have any questions about the course? Okay. If you don't have any questions, you are free to go. Have a great evening. And yep, and I will get on the email immediately to answer all your questions.
So I have on the last rubber band we did with the cup, that should have been like increasing linearly. Okay, then I got it wrong. My second one went way further. I mean, it did go further than the third, but from the first to the second, it increased a lot more than from the second to the third distance.
That could be due to the rubber band itself. It could be the elasticity, or it could be that somehow you just pulled it a certain way that it just went.
Okay.
It could also be how it hit inside the cup. So there's lots of reasons that wouldn't work, as long as you know why it didn't work. I'm more interested in that than whether it worked or not.
Okay.
Okay.
Okay, thank you.
And Kathy, you need to stop stressing over this.
Yeah,
You're very
well,
sharp. I know that because I've seen your work. So you shouldn't be thinking you are so confused, because I don't think you're as confused as you think you are.
well, thank you. Can I go back and fix that other? I mean, I don't know that. Well, I'm just going to leave it. If I got it wrong, it's okay. So,
Okay. If you want to go back and fix it, go ahead. I haven't graded any of that yet. I'm still waiting
okay.
for, if I don't have more than half of the assignment in, I don't touch it because I need to wait. I'm still
Oh,
waiting for people to finish up the linear motion module that was independent study.
hmm.
And I still have people that haven't turned in anything for mastering physics. And I have a lot of students that haven't turned in any labs at all. So we're
Okay.
way ahead
Wow.
of the game.
Okay. Well, I might repeat that experiment and see what happens.
Well, you might
Okay.
as well, since you're already going to have the rubber band and
Yeah,
shooting balls at things. You might as
true.
well just say, okay, well, let's see what happens when I let go and it goes into the cup.
Yeah. All right. Thank you.
You're welcome.
Good night.
Good night.
Hi,
Hi.
uh, I'm Dina. So I wanted to make a meeting, but I hadn't just had never. But I am worried about my course if I'm like, because I want to be sure about my gradings.
Okay.
Uh, I don't know if you can check um if I'm doing my work, everything on mastering
Yeah,
physics.
I can check right now. Let's see here. Okay. I have everything in for you in mastering physics.
Okay.
And you are one of the few people that has everything in. Um, there's only 3 of you that have turned everything in. So congratulations. I love you.
Okay. Thank you.
So let me check everything else.
I know the labs, in the beginning, I was like submitting in the mastering physics, but I wasn't sure because we had the other class, and the other class, it does, as you said in the beginning, that,
Yeah,
that
there you have to a lab component and you have the regular class. And I have all the assignments in the regular class.
yeah,
So you don't need to go to the other class. You can submit everything through the one class.
okay.
Okay. It doesn't matter which one you submit it to. I grade it and then I put the grade into the course it needs to be in. So if you submit it in the regular course, I take that grade and I enter it in the course, but then I also enter it in the lab. And it doesn't count for anything in your course, the lecture segment, but it counts 100% in the lab segment. Okay? So as you do the labs, they get put into the grade book. So let's see what I have here. Let's see. Okay, your enrollment. Your dynamic study module is 100. So far, class participation from what I've entered is 100. Weekly discussion is 100. Participation so far is 100. But I haven't added all the rest in. So far, all the grades that I have entered, you have 100%.
Okay.
Yeah.
Yeah. Yeah. You need me anything?
So
Something.
let's see. Okay, so I haven't graded the vector maze lab. Have you done that?
Yes.
Okay. Um, yeah, so if you've done all the lab work, I'm going to be updating the grade book this weekend. You should be fine. And if you want, if there's something missing, I'll just email you and let you know so that you know what you need to submit to me.
Okay, yeah, because it had
Okay.
happened to other courses that sometimes
Okay.
about grading and then teacher sends me an email and I'll submit it again. Uh, yeah, so I appreciate everything as well.
Oh, no problem. I appreciate you being a hard worker and getting your stuff in. Uh,
Yes,
you're
thank you.
doing a wonderful job so far.
Okay, thank you so much, and I'll do this lab that we have.
Okay.
I mean,
And again, Tuesday, 6 to 7, just click on this Zoom link and I'm there for office hours.
all right, yeah, because I might have a question about
Okay.
perimeter, about the angles. It looks like,
Yeah,
and
what
I'm
I
interested
may
in
do is I may go ahead and make a protractor out of paper and upload that. So all you have to do is print it out. And that way you can
okay.
have a protractor.
Well, okay, I understand now. I think maybe, you'll give us a projector, the
Yeah.
sheet, and I'll place it on the table, and then I'll try to shoot it. Where's the angles at? Like, like
Yep.
the picture kind of thing.
The other thing is that if you don't have a way of shooting it, I don't have a rubber band here.
I
Yeah.
have
Oh,
a
wait a
rubber
minute, I
band here.
do. Here we go. Okay. So I just lost my rubber band. Let me get another one. Okay, these two are connected. It's okay. So what you can also do is something like this, where you can pull it back. Never mind, that didn't work. But if you take a cap off of a pen, it has this little groove on it. Okay. And then by doing this and stretching your rubber band across your two fingers, farther you can get them, the better. Okay. Then you can pull this back like this. Okay, don't don't shoot that in the house. But if you just pull it a little bit, you can get it to launch. Okay.
Okay.
So, and again, you already know what the answer should be based on your lecture notes. Just make sure that your answers come out the same. And if they don't, just say, well, I must have done something wrong with this. I really just want people to play around with launching things. There were so many options. Like I could have you do a virtual thing, but that's not the same thing. You know what I mean? So
Yeah.
if you want to set up a camera and kick a soccer ball around or throw a baseball or roll things off your table and videotape it, you could do that too. You see what I'm
Okay.
saying? So
Yeah.
be a little bit creative. I tried to make it as simple as possible so that you could just do it. Um,
Okay.
okay.
All right. Thank you so much.
Oh, you're welcome.
I got it. If I have any question, I'll send you email.
Please do. Please do.
Okay. All right. Thank you. I feel much better now.
Good, good. I'm glad.
All right. Well, have a great night.
You too.